Um, the triple scalar product is this. The triple scalar product is called this because you're going to multiply three vectors, hence triple, in a way that gives you a scalar in the end. So the three vectors we're going to multiply, we're going to call them u. And so my u vector is going to have u1, u2, u3 as entries. And then v, of course, is going to have entries v1, v2, v3. And then you guessed it, w is going to have entries w1, w2, w3. And so if you look at this, formula for the triple scalar product, you can tell that it's going to be a scalar because v cross w is going to give you another vector, but then u dot that vector is going to give you a scalar because the dot product always gives you a scalar, right? It turns out that all of these are equivalent, right? So there's 1, 2, 3, 4 different ways you can rewrite this triple scalar product. And so maybe the easiest way to compute is with the determinant of that matrix at the end, where the rows of the matrix are just the entries in your vectors. Notice, though, what does not work. It would not work if I did v dot u cross w. Why doesn't that work? Yeah, the cross product is not commutative. The cross product is anti-commutative. So if I put a negative sign out here, then that would work. Yeah. Or I could do u dot w cross v if I put a negative sign out front. And so what that means for us, since you can see this, is if we swap rows, in a matrix, what does that do to the determinant? Yeah, then the sign, the plus or minus sign of the determinant, changes. Right? So if I have this matrix and I just exchange rows 1 and 2, then it's just going to make the determinant negative. Yeah, and then whenever I swap them back, it'll be positive again. So, yeah, kind of a weird consequence here. And this theorem right here says the volume of and I don't even know how to pronounce this word. I see it all the time in books, but the volume of a parallelepiped with sides u, v, w is given by the triple scalar product. So what is that? It's like if you have a parallelogram with sides u and v, and then you make it three-dimensional by, throwing another vector in the mix. So this vector would be w. There we go. So it's a three-dimensional shape that has all the properties of a parallelogram. So all of the sides of this three-dimensional object are parallelograms, and so that's why we call it a parallelepiped. And so if you wanted to work this example, you just have to take the triple scalar product of A, B, and C. So that triple scalar product would be like A dot B cross C, but we know that the easiest way to compute this triple scalar product would just be to write the matrix 0, -2, -1, -2, -1, 0, and 2, -2, -2, and then take the determinant. So my determinant would be 0 times something, but it doesn't matter because that's a 0, minus negative 2 times, give you guys a second to catch up, but what determinant am I multiplying this negative 2 by? I'm looking for a 2 by 2 matrix. Perfect. Negative 2, 0, 2, negative 2. And then plus negative 1 times what 2 by 2 matrix determinant? Yep, okay. So then I'll leave off that 0. 2 negatives make a positive. And then what is this determinant, the first one? Should be 4, yeah. It is negative 2 times negative 2 minus 2 times 0, so that should be 4. And then plus negative 1 is just a minus. And then what is this 2 by 2 matrix determinant at the end? I think it's 6, because it's negative 2 times negative 2 makes 4, minus 2 times negative 1 is 6, yeah. So I have 2 times 4 minus 6, and so that triple scalar product should be 2. So that means if you use these 3 vectors to be the 3 sets of opposite edges of a parallelepiped, then the volume of that parallelepiped would be 2.